Today we're reviewing the RTX 4090 Neptune. It's a water-cooled card with a whole lot of VBIOS problems that are finally fixed now. That's why the review was so delayed, because this thing was not working anywhere close to normally out of the box, but it's working now. So at $1,800, it costs more, of course, than the 4090 Founders Edition. You can see we've wired a massive amount of thermocouples to it. There's actually a couple more that aren't in this group as well. And that was so we could test component thermals alongside the GPU thermals against the Founders Edition and see if it's able to punch through in a way that makes it worth the extra money. Before that, this video is brought to you by the Thermaltake Core P3 Pro open frame case. Back when we reviewed the original Core P3, we praised the case for its versatility as a standard desktop PC, a wall-mounted gaming machine, or a horizontal test bench for your testing projects. The P3 is back with updates, including an additional fan bracket, updated I/O ports, and better main compartment layout to give cleaner cable management pathways. Learn more at the link in the description below. So here's the deal with the colorful cards. First of all, colorful is pretty large in China, and they don't have a lot of distribution in the West, but they're kind of working on it. They have been for a few years. Who knows, with EVGA out of the picture, maybe there's room for someone to come in. So that's why, if you haven't heard of them a lot, that's probably why, but you're gonna hear about them more, at least in the coming generations probably. This card is the Neptune OC. It's the $1,800 model. They also have a model called the Vulcan. That one is $1,770. And then they have a normal reference model at $1,600 for their cheapest one. Now, externally, we're gonna talk about a lot of this in the teardown that's part of this review video, but externally, it's pretty simple. The aluminum housing does actually end up getting used for soaking some of the heat. Not an intentional use, but a good one, because it's a lot of metal, it's a lot of surface area, even if it's an unintentional use for it. There is a weird typo on the card. We'll kind of give them a pass for that, but it does say virtual instead of virtual. So attention to detail, not a strong point for colorful on their $1,800 video card. As for the rest though, pretty straightforward. So it's a 2-slot card. That is the most compelling aspect of this thing. The OCV does have an overclocking offset in software, so that's good and expected. It also, however, has this, which this is just I don't know, it's like a gimmicky way to do a dual VBIOS basically. So it does have 2 VBIOSes. Typically you'll see just like a simple switch up at the top where it's sort of left or right, and that's it. They're going for the button approach here, which is fine. It all does the same thing. So that's what that is. Standard output. It's got some holes in it that don't do a lot here since there's no active airflow on the card. And for the cooling solution, is using a 360mm radiator. You can see we've had to attach a tachometer sticker here where we used a physical laser tack to measure it, because this has no input back that we were confident in anyway for reading the fan speed. You get stuff out of GPU-Z, but we weren't 100% sure of it, so we measured it physically. And on the far side over here, there's a bunch of cables hooked up. So they're running all of these fan cables, actually fairly neatly packaged together here with this small zip tie. So that's a nice small attention to detail thing. Running all these daisy chains to each other down into this small PCB where it's kind of a white and then an off-white. Not the best attention to detail there, but for the fan headers. And then there's also 2 cables in here where at least one of those is an RGB cable. For the tubes, so they're running the rubberized tubing rather than the Teflon coated tubing. There's 2 main types of tubing for liquid coolers. The Teflon coated ones have better resistance to permeation of the tubes over time, which means there's less loss of liquid over time, loss specifically to permeation of the material. However, the Teflon option also is prone to cracking and also is not as flexible. So this is a rubber option, pretty common. There's nothing wrong with either one of them. They just have different advantages. And for RGB, there's a light bar in here, there's a light bar in here. They're layered in a way where you can actually see into the cards. Not the highest quality layering here, but that's what they did to get the RGB lights the way they did. Personally, I'd rather just have it be a block of aluminum, but if you want lights, I guess that's what you do these days. For the rest, cable, they're using an NVIDIA supplied adapter here. So this is the same one we tested in the review. And you can see it's a 12+4 in there. The back side's pretty simple, where we've got a back plate. We have direct access to what's going to be the pump block housing probably, and then a couple of Phillips head screws all around it. Now, before we get into any of the testing and the teardown, one really important point everyone needs to know with liquid-cooled cards, pump placement really matters on these. So we've done videos about pump placement with AIOs in the past, and with these, it's particularly important. I mean, it's in all the manuals and everything. Don't put the radiator in the floor of the case if the GPU is above it, because the pump itself is in the card. If you put the radiator in the floor of the case, which is an option in things like, say, the Lancool 216, although I don't think with 360s, and you've got the tubes pointed up, you are going to kill the pump. Probably within a year. If you're lucky, maybe 2. But that is a guaranteed way to kill the pump. Tubes at the top with the radiator at the front, it's not great because it's not the ideal configuration, but it's not guaranteed death of the pump. Tubes at the top, radiator at the bottom, card in the middle of the case, guaranteed going to kill the pump at some point. So don't do it that way. But let's get into the teardown, and then we'll go through the thermals and everything else, power consumption, all that. So we're going to go down to a Philips Zero, which is in our toolkit as well, on store.gamersnexus.net, where you can also, by the way, grab these brand new and amazing coasters. That's right. These are drink coasters. They are awesome. We made these, and we just launched them. They're on store.gamersnexus.net. Pick them up with a mod mat or a toolkit while you're taking apart your video card. Okay, let's track these. This is the first time I've ever used a 1.3 millimeter Allen head. And you can see how little tension was on it because I didn't even need the rest of the driver to get it out. Probably a good thing. I'll do this and put it back together too to prevent stripping it. Tension is good here. Okay. Sometimes I like to check these to make sure they've actually tightened it. No tearing up. There shall not be any tearing up here. It's kind of like one of those no loitering, no skateboarding, no biking signs at a shopping center. No tearing it up will be happening around this card. All right, there's the leaf spring. Interesting. Ooh, this is going to be kind of a pain. Okay. So we got some cables, some thermal pads that I need to preserve. Okay. You can see it's a little annoying because it's got an actual cable going into the board. Whereas if you just did a standard dual V BIOS switch, it would just be a tiny physical thing with no cable, but not the biggest deal. So first of all, for thermal pads, these are pretty large. These look to be about 2 millimeters. 2 to 2.2 from the surface of the memory module. So those are large thermal pads. Not a good thing. As long as they make contact, that's the important part. But thinner is better. On the back side, they had these 2 thermal pads contacting here on the plate. So either there's that's just the back of these inductors for the power delivery. So all these situated up near the 12 plus 4, they're pulling some heat away from the back of these. Here is the cooler itself. And we've got a lot more to look at here. We need to get on the opposite side of this and look at how the pump is situated. So first of all, for the cooler, it's a full copper plate. So they're making contact to all the same thing. And what this means is that your GPU is going to be sharing a cooling solution with the memory and with the VRM. And what that means is that since all of the heat is going to the same place, the GPU is going to run a little warmer than it would if it were only cooled by a plate here to the liquid cooler, but everything else will come down. Now, the alternative would be what companies have done in the past. They'll cool just the GPU, and then they'll hook all the rest of this up via base plate to the hybrid part, where you might have a small fan on the end of the card here. EVGA used to do that, and that would be how you would typically kind of load balance the liquid cooler so that it only has to focus on the GPU. It can use all of its cooling power for that, which would bring the temperature down a bit for GPU, but you get wider benefit here. In there, you can see the pump block housing. So that is going to be the pump. There's micro fins inside of that pump in the cold plate, and that's where all the cooling's happening, all of it, for everything on the board, because there's no fans on this thing. So all the heat's sinking into a cold plate that goes into that pump that you're looking at down there. So that thing right there is a copper heat pipe that you're looking at on the top side of the base plate, and we'll get a closer look at that later. So what we're gonna do right now for this video, we're gonna pause here. I'm gonna wire it up, we'll do testing, and then we'll come back, take it apart further. But it's all gonna happen seamlessly for you. And it will take 2 days of my life. So I'll be right back. Okay, it's been like a week. All the thermal testing's done. The card was all wired up for a while. Yep, there it is. And we've just reassembled that part of the card. Now it is time to look at what the flip side of this actually looks like, how it's assembled. Actually, you can even see NVIDIA's logo from the silicon imprinted onto the copper. That's kind of crazy. Okay, here we go. So this is part of the PCB for the pump. There's going to be a motor in there. It's probably, I don't know, 8 poles or something. This is kind of crazy, these extensions. This is ridiculous, actually. I've never seen pump housing exit into extensions quite this long for a computer part. So here's what we have going on here. They have heat pipes on the top, actually, not really going anywhere. So you've got an evaporator end and a condenser end. The evaporator is where the heat source is. The condenser is where the liquid inside the heat pipe, well, let's just say this is the evaporator, this condenser. The liquid will evaporate here. It'll travel up here as a gas. It'll recondense here, and capillary action brings it back down. So for this one, the heat pipe is connecting in a way where it's really just sitting over the VRM component. So you can see there's this plate that is, looks like soldered or welded to the copper plate. And on the opposite side of it, the heat pipe is going to be pulling heat from the VRM parts here and kind of just moving it over here, which is going to help a little bit with soaking some of it, but it's not really removing it from the solution. You're still sinking it all ultimately into this pump block and the microfins that are in there. Below that, they've got a custom PCB down here that's glued against the housing with some screws in for good measure. There's a custom shaped PCB here for the lighting, similar to what Intel was doing with Arc. This, I'm guessing this is just for an insulator to block contact with any of the exposed metal on the PCB for the pump to the housing, assuming it's conductive electrically and not just anodized or something. So that's probably all that's there for. And ultimately, in terms of the solution itself, it's pretty simple. They're just using a big copper plate for the memory and for the GPU. All of that is sinking, ultimately going to be cooled by the microfins on the flip side of this, which is probably going to be copper sandwiched with copper. And then the upper plate here is for inductors. You've got MOSFETs and capacitors in here. And it's a pretty simple solution. There's not full coverage water, so the water's not flowing through all this stuff. It's not flowing through where the memory is. That's fine. That's normal for an AIO hybrid approach solution. But it does mean it's a little less efficient. I think I'm going to go ahead and do one more step. We're going to take all these screws out. That'll be fun. And just see kind of how it pulls apart, because we're not going to have any leaks from this. And these I'm going to separate. They actually show you the flow direction on these too. So the one I'm working next to now flows out, goes that way, and this one comes back in. All right, well, I don't think I'm going to really be able to get this fully out of here without also unscrewing the pump. Oh, maybe. All right, well, you can see it clear enough. So here's what's going on. For these two plates, in order to have good contact, they need them to interface with each other. I was thinking maybe solder or welding. That's the cleanest way to do it to get the best contact. What they've actually done is put a very tiny amount of thermal paste all around the inner side, here, up here, 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 and they're using that to form a contact between the two copper plates so that some amount of the heat that is being absorbed here from the memory and from the GPU core end up in this plate. And then that plate, ultimately it's all going to the same place. It's just that this is sort of a secondary layer. It's less directly connected to the GPU core where the cooling really is, and that's getting somewhat dealt with by the heat pipes. Yeah, there's not really anything to see under there, so we're gonna leave it as is. Okay, back to the testing. So now we're gonna get into the thermals for this. We run the test before tearing it down, and then we do additional tests after the teardown, and we replace any of the damaged thermal interfaces with like for like so that we can do the testing. So this massive thermocouples, these are hardwired in, and we secure these so that we can get memory thermals, MOSFET thermals across multiple MOSFETs and memory modules, and then take a better look at, does this thing cool more than just the GPU? The GPU is really easy to validate. You can use software for it. So it's unlikely that a manufacturer will ship something that has very poor cooling on the GPU, because any end user can validate it. MOSFETs and memory, though, different story. That's where we've seen things really incinerate, like the Zotac ones in the past, for example, where they had these gigantic heat sinks that weren't even making contact with the VRM components. So for this, we assigned thermocouples to the same memory modules we tested on the Founders Edition, and because the MOSFETs themselves are a different spec, we don't have a pure like for like, which is normal, but we assigned thermocouples to similar placements for where we expect the hottest MOSFETs will be, so that we could test how well it cools versus the FE card. And that's where we're starting for our partner comparisons here. So for this kind of testing, we typically also noise normalize it, where we run at a fixed dBA level at 20 inches distance. And that's so you can't just brute force the fans to get to the top of the chart, because you're not accounting for the noise, which is a very real aspect for users, because it's a very human and subjective thing, unlike temperature where you don't really see it, so you can get away with a little bit warmer, but not with an annoying noise level. So normally we noise normalize. In this instance, out of the box, the FE card and the Neptune both run at 40 dBA at 20 inches distance when set to auto settings in our test workload. So perfect. That means the auto settings are already like for like. Here's the results at the same noise level and auto fan speed. The Neptune ran at 51.5 degrees Celsius over ambient, which is clearly advantageous for clock behavior if they build the VBIOS properly, because NVIDIA GPUs can boost higher under lower thermal constraints. The advantage is significant at 18 degrees reduced, and it's far ahead of the air-cooled FE. But of course, you're moving all of that surface area from the card into a radiator mount instead. The hotspot temperatures were about 15 degrees lower on the Neptune, also a big improvement as a result of the AIO solution. Memory temperatures aren't too different here, but they're also not directly passed over by the water. They are sharing a single block solution, but the water isn't flowing over it like an open loop, so they don't get all the benefit of water. The memory thermals had the Neptune 5 to 8 degrees below the FE memory thermals, and in both situations, we are well within spec. MOSFET temperatures are also good and in shape on both cards. Neither of them is anywhere close to a out of spec reading, and the Neptune didn't improve too much over the FE for this either. So the Neptune's biggest gains over the FE were in GPU temperatures, which is expected because the microfins are right on top of the GPU. So that's where you'd expect to see the gains. It's on an open loop card, and at 52 degrees versus nearly 70, it is a massive reduction. So there's still clearly room for partners here to improve on the FE. The problem is FE is getting really good now, and the price difference is still in favor of FE. Partners are going to have a really hard time competing on price with NVIDIA because they got the chipset cost, or probably close to it. So depending on how the business units work. So that's going to be tough for them to fight. Now, the improvement in frequency should be something that you'd see a lot of with a 52-degree reading. In the past, with 30 series, for example, you'd see something like 12 megahertz every 5 or so degrees Celsius, depending on where you are on the sliding scale. And that could add up fast. If you're running a specialized partner card versus a worse NVIDIA FE card, it might give you another 2% performance basically for free, just for running cooler. So that's what we need to look at with the Neptune. We'll get to that shortly. But one of the biggest gains you could get from the Neptune here is actually running the fans slower. So you could instead leverage that extra thermal headroom to reduce the noise levels of the card by bringing the fan speed down, and then you run the GPU core hotter, obviously, but it's so within spec here. You got 18 degrees to play with before you're even at FE levels, so you can really drive down the noise level. Just be careful not to drive the RPM down too much because they are pushing through dense fins, so static pressure will start to matter. This is also, unfortunately, where there's a bit of a deficit with the Neptune, though. We were not able, at the time of reviewing this at least, to control the fans through Afterburner or other standardized software that we basically always use. Colorful has its own software where you can tweak the card through there, but it's a bit of a pain in the ass to go through those extra steps just to control the fan speed, because what they're doing, they're running all the fans into these daisy-chained connectors, and then those run into a PCB that's on the board. That PCB has a connector that runs down the tubing within the sleeving, so it's concealed, and that runs into the video card itself. So since nothing ever plugs into a motherboard, you don't have standard motherboard control over it. You could do it that way yourself if you wanted to, though. You need extra cables, though, and it would be kind of ugly. But you got to use Colorful software. So a little bit of a downside there, but it runs at about 1230 RPM out of the box, and we validated that with an external tachometer as well. On for the next set of tests. This is for power consumption. We're measuring at the PCIe cables for this, so we're not looking at total system draw, but rather the individualized GPU power draw. The Neptune had a few different VBIOSes. This was a major downside for the card. It also created a huge amount of downtime for us because we had to rerun a bunch of tests, flash the new BIOS on there. So because of that BIOS toggle on the back over here, the original turbo BIOS didn't work properly. It was really constrained. It was actually worse than the stock VBIOS, and they shipped a new one, runs way hotter, way more power. So it allows you to clock it up higher, but if you bought this super early, you're gonna wanna flash that because yours did not come with the correct VBIOS out of the box. Here are the power results in FurMark. This is under a full load, so it's a worst case scenario. The Neptune with its stock VBIOSes ran at 441 watts with the button released and 457 with the VBIOS button pressed in. According to Colorful, this isn't expected behavior, and it was part of a known issue with the first batch of cards. Only one VBIOS is available to flash though, and it's the turbo one. The stock one worked as expected out of the box. The new VBIOS allowed us to pull 575 watts stock, or 604 when overclocked, whereas we were previously stuck with erratic behavior. Compared to the RTX 4090 FE, this is lower than the overclocked 4090 FE allowed, which isn't great because we have all this cooling potential, all the thermal headroom in the world, but we are becoming power constrained when trying to overclock even before FE. And at best, it's about the same as the FE when running stock. So a few issues here. First, in addition to the VBIOS stuff we talked about, it was severely bugged when we first got it, those VBIOSes, where we noticed that when overclocking the card, up until we flashed it, the power target would silently reset itself to 85%. So if you're not familiar, power target sliders, 100% is normal. You go under that, then you're gonna underdraw power. It will reduce performance. It'll reduce the temperature, obviously, and the power consumption. You go over it, you have additional headroom to pull clocks out of and run the performance higher. So this was silently dropping to 85%, where we'd basically go into the overclocking tools, apply power offset, apply an overclock, close it, and then you come back later and check, and now it's at 85% power, and you don't know for how long it was, but probably the entire time. It just looked like it worked the first time. So extremely frustrating. It was very problematic, especially because it was silent. The VBIOS appears to have fixed it. We haven't seen it again since then, but we still wanted to report on it because it's a concerning behavior, and it was clearly very buggy. I think they've had software updates since then as well, so maybe that's helped with it also, but something to look out for if you buy one of these cards. You really don't want to be screwing around with software bugs on video cards like this. I mean, that sort of stuff, it's not that advanced. Like, these options have been in software forever for video cards, so it really just needs to work at this point. Now, as for the power limit in general, the card isn't allowing us to pull as much as the FE, which isn't great because that constrains overclocking potential. We were able to get higher clocks on the FE card despite running way warmer. Seriously disappointing because this thing has all of the cooling option to push, but you just can't. They don't give you enough power. So anyway, that's probably partial feedback for NVIDIA and partial for Colorful here. Time to look at frequency. With the stock VBIOS, the Neptune ran at about 2720 to 2770 megahertz. If we plot the FE card, it's functionally identical to the stock Neptune. That's unfortunate because the Neptune should be clocking higher with that 18 or whatever degree reduction it had. Colorful didn't indicate any issues with this particular VBIOS, so this is stock behavior. This also means that there's no inherent advantage in gaming applications, so if we were to waste everyone's time and show a bunch of gaming benchmarks with these two cards, you'd see they're the same when it's on the stock VBIOS. So they've basically underclocked it, and then they're pulling more clocks out of the thermals. with the new Turbo V-BIOS revision and without an OC applied, at least an extra OC, the extra power consumption did actually go to use. The card pushed up to 2820 megahertz from 2740 previously. So at least that's an increase. And as a reminder, that's without us applying a manual OC. Our next test is for surface flatness. We took needle measurements from a calibrated 0 point and we present it as quartiles with depth in microns. Here's the chart. The most important thing on this chart is to have a compact box. The outliers extend to the top of the whisker protruding from the box, and the colorful Neptune's cold plate did really well here. The machining on the cold plate is extremely consistent. We've done excellently with it, and it had fewer outliers than other GPUs we've tested. So good job to Colorful on the cooler design. And then the last of this really just has to do with the case fit and the tube routing. So the tubes are fairly easy to work with. They are using the same type of tubes that you find in Asetek coolers. So that's going to be the rubberized ones. There's two types of tubes you'll find in AIOs. They're either an inner lining Teflon coating, and that Teflon coating prevents or reduces at least permeation of the tubes over time. So the Teflon coated tubes that are more rigid and harder to bend and manipulate, those retain the liquid a little bit longer over time because you're sort of hardening the tube inner wall against permeation and loss of liquid. However, they are prone to cracking. In this kind of application, they really suck to work with. Terrible because you don't get the maneuverability to manipulate the cooler to where you need it to be. So they've gone with the correct tubing for this, which is the more rubberized approach. And that has a little bit of permeation, but they still last like 5-6 years, these types of AIOs, in most cases without any concern really. And then you could refill it if you had to. But as for putting it in radiator spots in the case, one thing we noticed is that it's easy to accidentally twist these tubes within the sleeving here and not necessarily notice it immediately. And if you do that, you could kink the tube and cause some flow issues. So you really need to be careful with making sure as you're spinning these around to fit it a different way, you don't accidentally bind it all up and cause, I mean, you'll hear it. You'll hear the pump basically starving for water. So it's very obvious when it doesn't work well. Overall, so the cooler actually is excellent. It's really unfortunate that there were all the V-BIOS issues there were. We think they've mostly resolved them. Stock, they should probably rewrite that V-BIOS table as well to boost it higher. Whatever they're doing doesn't make any sense for the thermal performance. Thermally, this thing's doing great. So Colorful has done a good job at engineering the cold plate, getting good contact with the memory and the MOSFETs, all those temperatures well within spec. They looked really good even versus the FE, which was already pretty competitive, oddly for this generation. So they've got that. It's just they got to get the boosting better because right now out of the box, your performance is like the same as FE. Normally you get a couple % swing from board partner to board partner. Here you're not even getting that. So that's where they can improve. That is something that can be done through firmware. So it doesn't mean that the cards that have shipped are doomed. They can be flashed to be improved. Now, as for pricing, $1,800 puts you over the FE, of course, if you can even get one. Puts you over a lot of other alternatives as well that we haven't looked at yet. It is going to be pretty cool compared to all of those, unless they're water cooled also. So it has that advantage. The best way to take advantage of that advantage is going to be to run the fan speeds lower so that you can get a quieter overall build. So if you're looking for quiet, but you don't want to go open loop, something like this starts to make a lot of sense for you because you could drive down the noise levels, run up the thermals from stock, but still be below a standard air-cooled card. That's the real benefit in this, but otherwise, if you're in it for overclocking, there's some GPU fitness and silicon quality here, run to run, card to card, that we cannot possibly account for with a sample size of 1 for silicon fitness. We can account for the thermals. They basically should all perform the same unit to unit, but at least for ours, the overclocking was a waste of time. That's just all there was to it. The other two cards we've tried, actually, the 3 FEs and then the 1 Asus card are all doing better here, and the EVGA one. So very disappointed with the OC on this. Maybe it's silicon fitness, but that's it for this one. Thanks for watching. As always, subscribe for more to support this type of content, or go to store.gamersnexus.net to grab one of the mod mats that we used to tear this thing down. Thank you for watching. We'll see you all next time.